in the brain.
Hi, I'm going to assume that I don't need the microphone. Is that okay?
Yes.
I don't know exactly how this is going to go, but the idea of this talk is to try to create some connection between noise and learning. It's a subject that people have been thinking about a lot recently in the study of the motor system, and then to try to put that at some level in the context of the kind of Bayesian thinking that we've been doing here in the last couple of days. And I'm going to tell you a little bit about noise in the motor system, and then after that I'm going to tell you a little bit about how noise and learning are related, and then finally about learning in the motor system. So we're going to go from noise and learning to learning, and cover 3 experiments that I've done with different students in the process of trying to put together some sort of picture that says something out of all that. And on the way, if I have time, I'm going to talk a little bit about Bayesian statistics, which is, like we've seen several talks, different than using Bayes to try to understand the brain, but maybe important in and of itself as a way of trying to think about experiments. So you can't give a talk about motor systems without showing video of people doing some kind of sports. So when we think about noise in the motor system, you think about these people who do this same movement, over and over and over again. And even though there's these compilations of them just not getting it, because it's really hard to get your motor system to do the same thing over and over again. These are painful to watch, but they must be really painful to experience, right? There's 3 minutes of this. I'm not sure we want to watch the whole thing. Maybe. Anyway, you have to have a sports video, and so I put it in, and now we can go on and talk about the really interesting stuff, which is science. Oops, is he going to let me stop? Yes? No? I'm stuck. There we go. So noise is important in the motor system. Every movement we make is different than every movement we've ever made in the past, right? And one of the ways that you can think about that is that even though you have noise when you're trying to do free throws, you also have noise when you're doing really simple things like all of us do every day, lying in the MRI and making movements with a pen on a tablet, right? That's something that we do every day. And you see here, wow, that's some cool noise. You see here that the movements there are noisy as well, right? Every movement is different than every other one. And interestingly, is that going to be the whole talk? I'm sorry. Interestingly, should we go to the VGA thing? Is that going to make it better? Does it bug you guys? No? Okay. All right. So interestingly, each dot here is a subject, right? How much noise you have when you move your right arm is predictive of how much noise you have when you move with your left arm, right? So there's something about you which is noisy or not noisy, at least in that sense. And and that's true for direction, and it's also true for extent, right? So you can measure noise in different ways, how noisy you are in your direction, how noisy you are in your extent. And it's also true if you look at the peak velocity. So different components of the movement, you're consistent in your noise across your arms. If you look at, now we're looking across targets, so how noisy you are when moving to one target and how noisy you are when moving to another target, again, you are consistently noisy across the different targets, whether we talk about your left or your right arm. So people are noisy or they're not noisy, right? At least that's what you'd think, but it's actually more complicated than that because there's no correlation between how noisy you are in your direction and how noisy you are in your extent. So somebody who has very noisy direction may not have very noisy extent, and vice versa. And that goes for direction and peak velocity also, but it doesn't go... wait, I'm missing one? Oh, I did the same one twice. Ooh, that's kind of... So missing here is where you see that there's a complete correlation between how noisy you are in peak velocity and how noisy you are in extent, because those are both measuring essentially the same component of the movement, right? How fast you go and how far you go, that's the same thing in some sense. And so those two are correlated across people, whereas how fast you go and how accurate you are and where you're going, those are not correlated across people, right? So different components of the movement. And you know, if you can, you saw the guy in the MRI, so obviously we're going to go to brains here. If you can characterize the noise in the movements, you can also characterize the noise in the brain, right? So we have here 3 different subjects moving to this target, and what we're seeing is basically the raw MRI signal during their movements to these 3 different targets. To this one target, these 3 different subjects. And I think you can all agree that at least moving to this target, subject 23 has a more consistent pattern of brain response than subject 13. Right? Is that clear? And that's going to be true across targets. So here's subject 23 having a consistent response to each of the targets, whereas subject 13 has a noisy response to each of the subjects, to each of the targets. Right? This has nothing to do with their movements. I don't know who's the noisy subject in terms of movements right now. This is only their brain. Right? Your brain is noisy or your brain is consistent. And you can sort of extract, if you like, the variability of the subject to different targets. And you can ask, how correlated is the variability of the brain when moving to different targets? Right? Is my picture here a fair picture, right, across the population, or is it just 3 subjects I've chosen where their response to the different targets is sort of the same? And it turns out, now, you can ask this question lots of different ways, and I'm going to ask it lots of different ways. Right now, what I'm going to look at is only movements of the right arm. Right? How consistent is the left brain, and how consistent is the right brain? Right? And if you look in M1, you find out that the variability in M1 is similar. Right? So a subject who's variable moving to one target is variable also moving to another target. Both for the left hemisphere, where's my cursor? Both for the left hemisphere and for the right hemisphere, but say slightly more consistent for the left hemisphere. Right? And the same is sort of true, this sort of consistent in both cases, but slightly more for the left hemisphere. For both posterior parietal cortex, I'm going to use different letters to mean posterior parietal cortex, but I'm going to call it posterior parietal cortex throughout the talk to make things simple. Both for posterior parietal cortex and for premotor cortex. So for higher level motor areas, that's true as well. And maybe unsurprisingly, visual cortex has less of a difference. Right? But it is consistently variable. If we now look at movement to the left arm, right, asking the same sort of question, we find that the picture in M1 has switched. Now the variability is more consistent, noticeably more consistent, right, for the right hemisphere than for the left. Whereas for the higher motor areas, premotor and posterior parietal, it hasn't switched. Right? Variability is consistent in the left hemisphere, but not in the right. And again, perhaps unsurprisingly, visual cortex still doesn't care. So that's kind of interesting. Now we're going to do something really complicated. We're going to ask about variability in the hemisphere when the 2 different arms are moving. So how much does the variability that I have when moving my left arm predict the variability of my brain when I'm moving my right? And I'm going to start this time with posterior parietal cortex, and it's a little bit of a complicated picture. So what you're going to see in posterior parietal cortex is that if I know how variable left posterior parietal cortex is when I'm moving my left hand, I also know how variable it is when I'm moving my right. Right? Same amount of noise for the two different movements. Whereas my right hemisphere doesn't have that. Right? And in addition, knowing the variability of the contralateral hemisphere for the right arm doesn't tell you much about variability of the contralateral hemisphere for the left arm. So I can't predict across hemispheres. Visual cortex has the same picture for reasons I don't understand. Premotor cortex is actually consistent all the way across. Right? So if I know how variable it is, how variable left premotor cortex is in movements to the left arm, I'll know how variable it is for movements to the right. If I know how variable right premotor cortex is for movements to the left arm, I'll know how variable it is for movements to the right. And similarly, if I know how variable, I guess this might follow, left premotor cortex is during movements to the right arm, I also know how variable right premotor cortex during movements to the left. And strangely, in motor cortex, I get nothing. So motor cortex, knowing how variable it is for movements to the left arm, tells you nothing about how variable it is for movements to the right. Which I guess if you think about it might make sense, right? Each cortex is doing its own thing for motor cortex. And, maybe you're asking yourself, okay, so now I know that there is this idea of consistency in the movements, right? How variable you are in one movement tells you about how variable you are in another. And that I can decompose that into speed and extent and stuff like that. And I know that there is a specificity of the variability in the brain, right? The different brain areas are variable in noticeably different ways. Right, or are consistent in noticeably different ways when I look across movements. But what about the connection between the variability in the brain and the variability in the movement? Right, like that's the sort of the obvious, like that's why we started, right? So it turns out that there's really only one connection that we found. Only in the posterior parietal cortex do we get a consistent correlation of variability in the brain with variability in the movement. And then also only for extent. So while these variabilities are clearly important, they're not necessarily expressing themselves in the movement itself. So that's it. That's actually it about behavior, right? That's the first thing. That's what we're going to learn about noise in the motor system for now. And what did we learn? We learned that there's independent components of variance, right? That there's consistent variability within a component, that there's no correlation across components, and that some motor brain areas show consistent variability in some movements. Right? But correlation of behavioral and neural variability is only in the posterior parietal cortex. And actually from this whole thing, while I think it's all really fascinating, that's really the part that we're going to move forward with. That's the part that's going to matter at the end of the talk. Oh, shit. I got another one. I'm sorry. So we're moving from talking about noise to talking about noise and learning. And as you watch this guy do his thing, the thing you want to be thinking about is whether he would be better off with more noise or less noise in his system. I don't know if anybody's seen this before, but it's an impressive thing. It's about 5 minutes of video. We're not going to watch the whole thing. He's trying to learn this trick where he jumps over the 3 things and lands on the skateboard. And I'll give away the end because we're not going to be able to watch the whole thing. He gets it in the end, but it takes him a while. Right? It's pretty frustrating. So is noise helping him or not? It seems like he's doing the same thing every time. But obviously he's not, because it doesn't work out the same way every time. I mean, it does at the beginning, But eventually it starts working a little bit better. I think we'll watch till the first time he actually sort of makes it, because this is painful. I mean, it's days of it. Every so often he switches shirts, right? Which means that he went home, slept. Oh, that was pretty close. There we go. All right, so that's good enough, right? It's beautiful, right? Like I strongly recommend watching all 5 minutes. It's truly inspiring. So clearly, I mean, if we think about this guy with his video, with his skateboard, right? I'm just going to leave that there for a second. If we think about this guy with his skateboard, he clearly can't keep doing the same thing over and over again, right? If he doesn't vary what he's doing, he's never going to get it. And more than that, he clearly doesn't know what the right thing to change is. Because if he did, he would get it, right? So what he needs noise, right? He needs to be doing different things every time in a somewhat random fashion in the hopes that there will be some gradient, however small, that he'll be able to eventually utilize, right? On the other hand, it's also clearly true that noise is his enemy, because the more he can't predict what he's doing or can't figure out what he just did, the harder it is for him to figure out what the right thing was. Right? And we're going to actually learn that lesson now, sort of the science way, right? Boringly. But that's going to be the take home, right? That there are different kinds of noise, and we have to pay attention to how they're helping or hurting us. And this is following up on a discussion that's been in the literature in my field over the last couple of years that kind of got kicked off with this paper by Maurice Smith, where he claimed that variability was correlated with learning if you were very careful about which variability you look at. And this goes back to the idea that we had before of variability being decomposable into different components. And that's a really important thing to think about all the time. And so if you group your subjects according to how variable they are in the baseline, you see that the subjects who are more variable learn faster. See learning level here? There's the more variable group learning faster than the less variable group. Okay? And it even seems to work at an individual level where each dot here is a subject, and here is this incredibly complicated and sophisticated measure of variability that you can only figure out if you pull the supplementary figures out and sit down with them for like a few days, right? But there is something that you can pull out of variability which will be correlated with how fast they learn at the beginning. But you know, it's there, right? That's cool. There is some measure of variability which seems to be important for learning this particular task. This is a reaching task where they got perturbed and, standard. But that paper led Conrad Cording and his friends to publish a paper a couple years later where what they did is that they looked across... They looked across different experiments that they did in their lab, and they looked across different experiments that different people had done, and what they showed was that there is no consistent relationship between how variable people are and how fast they learn. Okay? So these are... it's clear what I'm showing, right? I don't need to walk through the figures. Okay, that's frustrating, but luckily they had an explanation. Right? They didn't just say, oh, it never works. They had a logic, which is connected to our skateboarder, about why it wasn't working. And the essential logic is that some kinds of noise are good and some kinds of noise are bad. And they separated it into two kinds. What we see here on the left in blue is how noisy you are. And on the right, I cut that off, is how well you're going to learn. Right? And what we see is that as you increase your observation noise, you decrease your learning rate. But, oh, there's learning rate. As you increase your state noise, you increase your learning rate. Very mildly. All right, what is observation noise and what is state noise? Observation noise is the noise that I produce in a particular movement that doesn't get fed back into the system. State noise is the noise that I produce which changes the state of the system and thus gets carried forward. Okay, and they put this in the framework of a common filter setup and learning like the kind we've been talking about. And I don't want to go into the details, right? You have a forgetting term and you have something which produces behavior, but critically you have some sort of learning equation where the state gets updated as a function of your behavior. And that updating is controlled by a Kalman filter constant K. And that K has an equation associated with it, right? Where this has something to do with the physics of the situation, but this is one kind of noise in the numerator, and this is another kind of noise in the denominator, right? The noise in the numerator is the state noise. It's the thing which affects X. The noise in the denominator is the execution noise. It's the thing that comes in when you go from X to Y. All right? Is that clear? So that's a prediction, right? If I can isolate state noise and execution noise, I should see learning go up with state noise and down with execution noise. And we used a model that we're comfortable with and familiar with and built an experiment around it to try to test that prediction. So the model is our version of one that you guys are all familiar with. There is a plan, right? And it gets updated. Well, let's start here. Yeah, there's a plan. I turn my plan into behavior. And on the way, I add execution noise. And then there's a perturbation, and the behavior and the perturbation produce an error. And that error gets fed back with some learning rate into the plan. But before I can go on, there's noise that goes from one step to the next. And then I take my plan, I produce my next behavior with noise, add the new perturbation, learn, and so on. That's the model. And that model has a number of parameters, right? And we're going to try to fit data from people who are actually making movements and experiencing perturbations to the model by estimating the parameters. And we're going to do it, remember I told you I was going to talk about Bayesian statistics, we're going to do it using Bayesian statistical estimation. And what that means is, so what are the parameters? There's, the ones that you think about, which is how much forgetting there is of the plan from one state to the next, how much learning there is, right? What is the state noise and what is the execution noise? But there's also the parameters of what was the plan at every given time step. So that's a lot of parameters. But there's actually more than that. Well, actually, hold on. When I fit these parameters, I'm going to sort of want A and B to be between 0 and 1. And one convenient way to do that is to actually fit these parameters and then pass them through a logistic function which takes minus infinity to infinity and moves it to 0 to 1. And that has advantages. In addition to allowing me to use sort of Gaussian variables, it also means that the difference between 0.9 and 0.99 is similar to the difference between 0.99 and 0.999, which is true when you think about learning and forgetting, but is not true down here, right? Where as you get closer and closer to 1, things get closer and closer together. Right? So it actually improves the sampling. But the third thing, the advantage, is that we can also have parameters that go beyond the subject. So we can say, what is the mean A across subjects? Right? So every subject A, here's S for subject, is being guessed from a mean across all subjects and a variance across all subjects. And that helps regularize, because if one subject is particularly noisy and it's hard for me to figure out what his parameters are, I will use information I have from other subjects to help me make a better guess about him or her. And so the experiment we're going to use with that is one where we have a long baseline, where there are a lot of trials where we got no visual feedback. And this will be, we will use the noise terms that we estimate from here, and then followed up by a set where I introduce perturbations that are changing all the time. And I'm going to use the learning that I estimate from here. So that way my estimates of the noise and my estimates of the learning are taken from different pieces of data to make sure that I'm not introducing spurious correlations between them. And I'm going to try to skip through this a little bit in the interest of time. Because this is a Bayesian estimation, I get a bunch of estimates. So here is one sample from the posterior distribution of the parameters. Here's a value of B, here's the two noises, and here's the X for that sample. And here's another sample for that same subject, slightly different B, slightly different noises, right? And while I'm estimating that, at the same time I picked this, I simultaneously got this, and at the same time I picked this, I simultaneously got that. In the end, I end up with many, many versions like this, 50,000, 150,000, and many, many versions like this, right? So I get a bunch of samples from the posterior distribution of possible values for B and sigma and X. Right? And you can sort of see that. You can draw, these are 15 different estimates of the state. This is 150,000 different estimates of B. And the same thing for subject 2. And then we have that for all the subjects, right? Here's all the different estimates of B for all the different subjects. And this is the estimate of the population parameter, right? What is the mean across subjects? So having all those samples actually gives you a lot of power, because you have lots of examples of what the right answer might be and how they fit together. And what we see is exactly what we were supposed to see. The planning noise seems to be correlated with learning. So this is individual subjects and the noise in their estimates. And what I've done here is I've taken all the samples across all subjects, so that subjects with more certainty weigh more and subjects with less certainty get spread out. And you can see that there's, maybe it's not huge, but as the state noise goes up, the learning goes up. What's that?
I didn't understand the sampling together story.
So, I'm going to go back to here. Okay? What a Bayesian black box does for you, right? Like there's packages and what they do for you. And you can do this yourself if you want by just coding it yourself. But we generally use a package that does it for us. Is that it produces many, many X's, an A for each subject, a B for each subject, noise for each subject, and the population parameters as a vector. And then it produces another one and another one. Many, many like that. And the idea is that if you think of the joint posterior distribution, right? So there may be correlations in the posterior distribution. It may not even be, it may have funny nonlinearities in its shape, right? That's all going to come out because these guys go together, right? The B, this A and this B and this sigma and this sigma and this X, they all fit together, and they fit together with this other subjects so that they're consistent with the population parameters. And the next guess will be slightly different, but again, they'll all fit together as being a sample from the joint posterior distribution.
So this is across all subjects?
Across all subjects, right? And so, like I said, what you get is you get information passing between the subjects, right? The parameters that I picked for this subject have to be consistent not only with his data, but also with my guess about the population parameters, which have to be consistent with all the other subjects' parameters, which are again consistent with their data. So you're requiring all those things to happen at once, right? Sample after sample after sample. And then you can look at how the samples vary, right? Knowing that you've sampled them from the joint posterior. You have a real picture of the joint posterior in whatever way you want to look at it. Does that make sense? Right? And so this is all the different simultaneous choices for sigma and B across all subjects. All right? So if there's no way. I mean, this and then this and then this, maybe. And similarly, the peak is very strong, but if you look right off the peak, you see that there's a clear shape here. There's an inverse correlation between execution noise and learning. And now X and Y are on the same scale. There's a predictive, the optimal common gain, like we saw in the Cording paper, is predictive of the actual learning rate, right, in the same units. So that the claim is that we've successfully separated the two different kinds of noise and shown that each of them correlates with the learning in the way that it's supposed to. So how far have we gotten? We learned in part one that variability is consistent across subjects, that the correlation of learning and noise is apparently only there in the posterior parietal that we could see. And in part two, we learned that learning is correlated with state noise, inversely correlated with output noise, and predicts the Kalman optimum. I'm sorry. Just a sec. So, no, I do want to see it. So, I used to row. It's a really lovely sport. But when you think about noise in the motor system, right, it's clear that sometimes noise is not your friend, right? Like you're supposed to be able to learn to get to a point where whatever noise you're making, it's not getting in your way, right? And I could watch this for hours, but unfortunately, Fred keeps telling me that I'm going to run out of time soon. So we'll stop here. And I'm going to tell you about one last experiment. And I'm going to have to do this sort of quickly. We're going to use MRI to try to localize learning. Where's adaptation actually happening in these perturbed reaching movements? And the trick here, again, we have a subject in the MRI with a tablet. The subject moves to 4 different targets and learns an adaptation such that after the adaptation, if the target is here, they're moving to here. If the target is here, they're moving to here. And if the target is here, they're moving to here. That creates a confound between the movement and the target that we're then going to try to leverage to figure out what is coding what. And the way we're going to be looking at this, I'm going to skip over this, but there's this idea of multivariate analysis where what we're looking at is the pattern of activity and trying to figure out if there's information in the pattern of activity about the target that you're going to. And perhaps unsurprisingly, if you look at baseline movements, or if you look at the end of rotation, or if you look at the end of washout after they go back to normal, it's really easy to decode what movement they're about to do in the baseline by looking at all the other baseline movements. That's what this says. And it's true if you look at visual cortex or if you look at M1. Right? That there's information about the target in visual cortex. And there's information about where the hand's going in M1. And you can decode them. And it's also true for posterior parietal cortex and for premotor cortex. But the interesting issue is now I'm going to try to decode what's happening at the end of the rotation based on the baseline movements. And I've got two different ways to do it. I can either use the baseline movements that are appropriate for what I'm seeing, or the baseline movements that are appropriate for what my hand is doing. Right? So the question is, when I'm over here after I've learned, is my brain activity more similar to the brain activity here during my hand movement, or to the brain activity here during the target appearance? And what we see, for instance, is that for the visual cortex, it's pretty easy to predict which target I'm looking at here by looking at the target activity here. And for M1, I'm going to do a better job predicting by looking at the hand movement here by looking at the hand movements here. And for premotor, like with M1, I do better predicting hand movements here if I look at hand movements here. But interestingly, for parietal cortex, I can't tell either of them. Now, importantly, it's not that parietal cortex has gone to sleep, because when I look at the end of the washout, where again movement and hand come together, I can predict its activity quite well based on the baseline. Right? So it's only during the learning, only when the hand and the eye are doing different things, that all of a sudden parietal cortex activity reflects neither this nor that. And I'm going to skip over the slide. If somebody wants, I have it at the end, where I try to convince you that it's actually doing something that's in the middle. Right? And that leads us to our final summary. Right? Where what I take home is really pretty simple. One is that learning is well predicted by the optimal Kalman gain, balancing state and output noise, and that the posterior parietal cortex seems to play an essential role both in the learning and in the production of the behaviorally relevant noise. Right? So it's the place where this planning happens, I'm claiming, and where the noise in that planning then gets turned into behavior. So that's the take-home message of my talk. And I want to thank Shlomi, who did all the MRI work, and Rick, who did the whole experiment on the noises and the learning and the modeling. And Ilan Dinstein was Shlomi's co-advisor, and Martin Franz and Lud Sellis were Rick's co-advisor. And, I have one more of those. Oops. Nope. There we go. I had to do this, right? This is with music. I don't know, when I do Aikido, there's never music. I think it looks so much better with the music. All right, I could, you know what, let's just turn it. All right, questions?